Okay, so ended last time and kind of run out of time. So let's talk about this real quick. So this was 4.762 times 10 to the negative 14th on the one on example 7. And so that was a frequency. Now, if you look, the number is very large, right? So this is a particularly big number. But then if we look at the wavelength, right? So let's look at the wavelength. It was particularly small right here. And so those are going to go in opposite directions. And that's what I was trying to say at the end of the video last time, and I ran out of time, is that it makes sense I have a really big frequency if I have a really small wavelength. And that's what was going on here. So we were just sort of comparing the two. Okay, so this next question here is pretty straightforward. All we're doing is we are using the energy formula, which uses Planck's constant, and that's all in the data booklet, by the way, so you don't have to ever memorize these. So we're going to be using this formula. Energy is going to equal Planck's constant multiplied by frequency. Now, if you look at this example 8, it says we have a wavelength of 698 nanometers, and we're looking for energy. Well, the problem is that we want energy. We have Planck's constant, so we've got this value, but we don't have this value. So we're in trouble. We have two variables. So what we'll do is we'll use our speed of light equation, and we'll go ahead and use our wavelength, and then that will get us a frequency. Okay, so let's go ahead and plug this in. Obviously, it's basically the same thing that we did above. We're just going to add a piece to it, so we'll rearrange our formula. So our frequency is our speed of light over our wavelength. Again, we don't want to use these nanometers, right? And so our 698 nanometers, we need to get those into regular old meters, and we're going to do it the same way we did in the problem above, and it's going to give us a very similar answer because we're going to get that 6.98. Let me draw an arrow here. That's going to get us the 6.98 times 10 to the negative 7th meters. So now that'll play nicely in our formula. So let's get a little more space here. So let's go ahead and plug that in. We can put our 3.0, actually let's go 3.00. Times, so it's the same as we did up here, right? And so, actually, let me get a little bit more space. Looks like I'm going to run out of space here. So let's clean that up real quick, and then that'll help me out. Okay, let's try this again. So let's go. Our frequency equals our speed of light divided by our wavelength. So that's going to be 3.00 times 10 to the 8th meters per second. Now again, that is provided in a data booklet. You don't have to ever memorize the speed of light. And then there's the value that we figured out, 6.98 times 10 to the negative 7th. And then this is going to give us our frequency, and then that's going to allow us to do our Planck's constant, or our energy equation. Okay, so go ahead and let's plug it in, 3.00, and I'm doing it right now, to the 8th, and divided by 6.98 times 10 to the negative 7th, and make sure you put the negative in there, and then there we go. I got I got 4.30 if I go with the correct sig fig. So 4.30 times 10 to the 14th, and then that's hertz, which is per second. So now we're going to plug that into our energy formula. So let's go ahead and clean up some space again. So we'll get rid of our conversion, so you already have that written down. And now we can plug that into our initial formula, which is right here. And we can get our answer. So let's go ahead and do that. So it looks for energy. So energy equals Planck's constant. You don't have to memorize it. It is right here. That's going to be 6.63 times 10 to the negative 34th. And there's your joules per second, right? And so you see the energy piece, that because this is going to be an answer in joules, and then we're going to multiply that by the 4.30 times 10 to the 14th hertz, and then this will give us our final answer. So let's go ahead and plug it in, and looks like it should be 3 sig figs because of that again. So let's go and do it. So I'm going to plug it in, 6.63. And you guys should have a calculator while you're doing this. Like, don't just rely on what I'm doing. And we're going to multiply that by 4.3 to the 14th. And then I ended up getting 2.8509 times 10 to the negative 19th. So probably going to go with 2.85 times 10 to the negative 19th, and then that is going to be joules. And so that's kind of what we're trying to do, is just try to run it through and be able to track the units, and then there we go. Again, this formula is provided in the data booklet, as is the value for Planck's constant, as is the speed of light and the speed of light frequency wavelength relationship. So just remember, main thing to take away is wavelength is going to get bigger, frequency is going to get smaller, and then the inverse, if wavelength is smaller, frequency is going to get bigger. And then also remembering that frequency and energy are the same thing, and so you're basically looking at 3 values and just how they compare to each other. Okay, so here we go, electromagnetic spectrum, and I touched on this earlier, but remember, this is the only part of the electromagnetic spectrum that we can actually see with our eyes, and that's just going to be the visible part. There's a lot more going on than just the visible part. And so obviously you cannot see radio waves, infrared from like your remote control at home. You're not going to see x-rays happening a lot, but if they were, you're not going to see those. You can't see the ultraviolet from the sun. And so there's a lot of energy going on out there that you guys are not able to perceive with your eye, but it does exist. Now also look at how the relationship here, you can see, okay, the over here we've got these really, really big, huge wavelengths, but then we have the safest type of the electromagnetic spectrum, radio waves, not dangerous like at all. And then over here, when our wavelength is really little, you can see things are more dangerous. And so that's just sort of the high energy is on the right, low energy is on the left, and that kind of goes with all of our stuff. Now here we go. Here's our visible light, and you can see the things, the parts of it we can see. And also if you remember your rainbow stuff from elementary school, your Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, you'll notice that the highest energy of them is the violet. So think ultraviolet, right? That's the higher energy. And then the infrared is the red there. Red is the lowest energy. So that kind of gives you a little something that Roy G. Biv could come into play. Now, they do have a lot of the stuff in the data booklet, so they're not going to obviously have Roy G. Biv, but they do have some information on the electromagnetic spectrum in the data booklet. So again, not all this has to be memorized. This is the kind of question you a lot of times will see on the test where it's just kind of like lows and highs. So this is a great question. So pause this, see if you can figure it out, and then resume the video and I'll give you the answers. Okay, so hopefully you pause the video. If you haven't, you're just sort of waiting on me, which I mean, guess is okay, but you're not going to be testing yourself much. So gamma ray, well, that's going to be high energy. Like that makes sense that that's high energy. Those are the dangerous parts of the radiation. These are the ones you have to be worried about. And then over here, the frequency, remember, is the same as energy. So these two columns are going to be the same. So gamma rays, the dangerous radiation, the thing you see in the movies, that's the dangerous stuff. And so since it's got the high energy, the high frequency, then it's going to have a low wavelength, or this is often considered, instead of lows and highs, considered a short wavelength. But lows and highs, I mean, same concept. These are going to be inversely related. Now, the violet light, if we're just comparing, now this is just comparing our visible light. If we're just comparing visible light, then we could consider the UV a higher energy. I'm not saying it's high, but it is a higher energy, as the red is going to be the lower energy. Now that's just comparing the two, right? And so you would not consider red light or violet light. Actually, they're dead in the middle of the UV spectrum. But in consideration to each other, right? Like we're looking at them as you would just look at each other. This is a pretty common test question right here where you compare the parts of what you can see and then you compare how they relate to each other. And then the radio waves, of course, are very safe, and so they're going to have extremely long wavelengths, and then their frequency or energy is going to be low. Now this is definitely low no matter what you're comparing it to. So this is a good test question type of concept, just the relationship between those. I've seen this a lot in the IB questions. And so this is a test question type thing. So just make sure that you can do that. It will benefit you on the test. So again, do try to point these out as we go to kind of help you out. Okay, just a minute and a half here left, and so we're probably going to stop here. Next thing we're going to get into is pretty academic, but when you get into these visible line spectra, like there's a lot going on that IB does test about. So again, key takeaways from this, just be able to fill in a chart that looks like this and be confident with the relationship where, of course, the energy and the frequency are the same. They're going hand in hand.